Hey guys, and welcome back to another lesson. Today we're looking at similar triangles. And I'm hoping that you're looking at the cover page right now and thinking, similar. These cats look quite similar. They're the same type of cat. They've got the same kinds of markings and everything. Maybe one cat's a little bit bigger than the other, but yeah, I think they're similar. So if that's your line of thought, you're off to a great start. However, there's a little bit more to mathematical similarity than just that. And triangles are a much simpler shape to compare when we're talking about similar shapes. So let's get into it. Now, I'm sure you'll agree that learning the anatomy of a cat might get a bit complicated, but surely we can learn how to name the different parts of a triangle. There are many ways we can do it, so let's just go through the ones that you're most likely to see on various exam questions. We could name the side lengths and angles of a triangle depending on what they are opposite. So for example, in this triangle, I've labeled this side length with a lowercase a because it's opposite the vertex or corner point of this triangle, which I've labeled with a capital A. Sometimes we call the angle at that vertex capital A. In the same way, I've labeled this side length over here with a lowercase b because it's opposite this vertex with a capital B. And I've labeled this side length here with a lowercase c because it's opposite this vertex, which has a capital C. So that's one way we could label our side lengths and our angles. And we often use this when we talk about the sine and cosine rules. So definitely take a note of that and keep that in mind. You will see it in future. Another way that we often name our side lengths is by using two letters and a connect the dot method. For example, side length A could be called BC or CB because, of course, side length A, which is here, is drawn by drawing the line between points or vertices B and C. You could say B to C or C to B. The direction doesn't matter when we're just talking about a length. However, when we get into vectors, it does matter whether we're starting at B and going towards C or starting at C and going towards B. But again, a length is just a distance. It doesn't have a direction. Now, having seen that example, I'm sure you could guess at the two-letter name for side length B and C. Length B, for example, could be called AC or CA, because of course side length B falls between the vertices at A and C. And again, the direction for a length does not matter. Finally, side length C could be called AB or BA because C falls between the vertices at A and B. You'll also see that they often use this connect the dot method to name angles. That requires three letters to represent each angle. For example, the angle that we see here at the vertex A could be called BAC or CAB. That's because to make an angle, you need to draw two lines. To make angle A, we need to draw the line BA and then the line AC. Or going in the other direction, we could start with the line CA and then draw the line AB. The order doesn't matter, but what does matter is if we're talking about the angle at vertex A, the A needs to be the middle letter in the three-letter name for that angle. Having seen that example, I wonder if you could write the three-letter name for the angles at vertex B and vertex C. Angle B could be called angle ABC or angle CBA. So long as the B is the middle letter, it should be fine. And angle C could be called angle ACB or angle BCA. Now that we know the different ways that we could name our side lengths and our angles, let's go into the different rules about similar triangles. These three triangles, triangle ABC, DEF, and PQR, are all similar triangles because these triangles all have equal corresponding angles. That's not to say that all angles of each triangle are equal. They're not equilateral triangles, but all triangles have one angle which is labeled X, one angle that's labeled Y, and one angle that's labeled Z. using the same letter to represent some value in a question means that that letter represents the same value throughout the whole question. So the angle labeled x here tells me that angle BAC is equal to this angle labeled with an x at angle EDF, and that's also the same as this angle labeled with an x at angle QPR. So I've got x's in all three triangles, I've got y's in all three triangles, and I've got z's in all three triangles. So these are similar triangles as they all have the same angle measures. Note, however, that I didn't need to tell you what any of these angles actually are. I'm just telling you that they are equal to each other. In fact, I don't even need to tell you all three angles of a triangle. If I tell you two of the angles in a triangle, you can work out the third angle of the triangle, because we know that the angles in any triangle must add to 180. Knowing that two triangles have two angles which are the same means that they must also have that same third angle. Let's try an example. Are these triangles similar? Well, to prove that they're similar, based on the only rule we've learned so far, we have to show that they have all corresponding angles equal. And looking at the given information, I can only see that they have one corresponding angle, which is equal. Angle BAC and angle EDF. The other angles that they gave us are not the same. However, having been given two angles for any triangle, I can work out what the third angle is. So I wonder if this angle is 45, and I wonder if this angle is 22. So for triangle ABC, I can find the angle ABC by knowing that the sum of the angles must be 180 degrees. I already know the other two angles, 113 and 22. So angle ABC must be what's left over. 180 minus the sum of 113 plus 22. That's 180 minus 135, which is 45. So I'll label that on the triangle. And note that it's the same angle as on triangle DEF. So having two angles the same, I should already know that these triangles are similar. But let's do a little bit more working to really prove to you that they have all corresponding angles equal. I need to find angle DFE or EFD, and I'll work that out by knowing the sum of the angles must be 180, and I've already got two of those angles. They're 113 and 45. So EFD must be what's left over when I take that sum away from 180. So 180 minus 158, and that leaves me with 22 degrees. So both of these triangles have all the same corresponding angle measures. And yes, they must be similar. Now don't worry about the side lengths here. We can see that triangle ABC is definitely bigger than triangle DEF. However, if they were the same shape and the same size, that doesn't make them similar. That makes them congruent. Similar triangles are the same shape with the same angle measures. However, one is an enlargement of the other. So similar triangles must have all corresponding angles equal. Now let's focus on the side lengths. Look at these similar triangles now. You can see that they all have the same angle measures x, y, z, but they all have different side length measures. The important thing about similar triangles is that the ratios of the corresponding side lengths are equivalent. So for example, in triangle ABC, I've got side length A, which is 9. I've got side length B, which is 21, and side length C, which is 12. And in triangle DEF, I've got side length D, which is 3, and side length E, which is 7, and side length F, which is 4. And in triangle PQR, I've got side length P, which is 6, side length Q, which is 14, and side length R, which is 8. Now I'm not saying that these are equal. Note this equal sign's got 3 lines to it. That doesn't mean they're equal, it means they're equivalent. That means I could simplify each of these ratios and they would simplify to the same equivalent ratio. Look at the first ratio. All 3 values there could be divided by 3. 9 divided by 3 is 3. 21 divided by 3 is 7, and 12 divided by 3 is 4. This middle ratio here is already in its simplified form. There is no common factor apart from one that they could all be divided by. And this last ratio here, all values could be divided by 2. 6 divided by 2 gives 3, 14 divided by 2 gives 7, and 8 divided by 2 gives 4. So all three of these ratios are equivalent to the ratio 3, 7, 4. Another way that we can compare the side lengths of our similar triangles is to remember that one shape is an enlargement of the other. So we'll compare our corresponding side lengths to find the scale factor of enlargement. So here I've shown that side length A on my triangle ABC corresponds with side length D on my triangle DEF. Now that's because side length A is in between the angles Y and Z, and side length D is also between the angles Y and Z. So those are corresponding sides. Although we know they're not the same size, D must have been multiplied by some scale factor to make length A, or A must have been multiplied by some fractional scale factor to make side length D. The same thing goes for side lengths B and E. They're corresponding because they're between angles X and Z. And side length C and F are corresponding because they're in between angles X and Y. So as I compare all of these fractions of my corresponding side lengths, they should be equal to each other. I get a common value K. That's my constant scale factor of enlargement. Let me clarify what I meant by scale factor with an example. In example 1, we proved that these two triangles were similar because we found all of the angles of both triangles and saw that the corresponding angles from each triangle were equal. Now that we know which angles correspond, we also know which side lengths correspond. For example, side length BC in triangle ABC corresponds with side length EF in triangle DEF because these are the side lengths that fall between the 45 and 22 degree angles. So if these two side lengths correspond, I can write a fraction of either 18 over 12 or 12 over 18 and work out my scale factor of enlargement. So let's do that. 18 over 12, which is 1.5, must be my scale factor of enlargement. What that means is that triangle ABC is an enlargement of triangle DEF by a scale factor of 1.5. That basically means that the side lengths of triangle ABC are 1.5 times the side lengths of triangle DEF. We know that that's the case for the two side lengths that we just compared. 12 times 1.5 gives me 18. So that must be the case for all of the corresponding side lengths. So I know that side length DF, which is between the 113 and the 22 degree angles, must correspond with the side length AC, again between the 113 and the 22 degree angle. And to find out what length AC is, I simply need to multiply its corresponding side length by our scale factor 1.5. 4 times 1.5 gives me 6, so side length AC must be 6. Now to find the missing side length on triangle DEF, we may want to find the scale factor that takes us from ABC to DEF. If a shape has gotten smaller in size, we still call that an enlargement, but the scale factor of an enlargement will be some decimal value less than 1. Because when you multiply by a value less than 1, your result is smaller than what you started with. Rather than doing 18 divided by 12, we can do 12 divided by 18. 12 divided by 18 as a simplified fraction is still 2/3. And I'd rather keep this as a simplified fraction, which has not been rounded, than write 0.6 or 0.67 or 0.6 recurring, because I can work with fractions accurately and exactly while working with rounded answers will give me a rounding error. So if the scale factor that takes me from triangle ABC to triangle DEF is 2/3, we can say that triangle DEF is an enlargement of triangle ABC by a scale factor of 2/3, which is less than 1, so that explains why it's gotten smaller. Let's use that scale factor so you can see that when I work out side length DE, which is between the 113 degree and 45 degree angles, it is corresponding to the side length AB, which is 9 between the 113 degree and 45 degree angles. 9 times 2/3 is exactly 6. So side length DE must be 6. So far we've learned 2 out of 3 of the rules about similar triangles. One rule is about the angles being equal. The second rule is about the sides being proportional, and they help us to find the scale factor of enlargement. And our third rule, you may recognize from our SAS rule for congruent triangles. However, for congruent triangles, we needed to have the same side lengths and the same angles. For similar triangles, we just need to have the same angles and have the same proportionality for the side lengths. So we may not know all angles or be able to compare all corresponding sides, but if triangles have one matching angles and the sides on either side of it correspond, that is, they share some common factor, the scale factor, then we could say that these triangles are similar. So in this example here, I've shown that these two triangles both have a common angle, angle X, but all the side lengths seem to be different. Triangle ABC has side length A, B, and C, and triangle DEF side lengths D, E, and F. However, I've labeled over here that side length C is equal to F times K, and side length B is equal to E times K. That makes me think that these two triangles may be similar because side lengths C and B are on either side of angle X, and C is some multiple of side length F, and B is some multiple of side length E. If I were to compare my corresponding side lengths, and I'm putting this in quotations here because I'll find out if they correspond by comparing these fractions, B divided by E should be equal to C divided by F. And in both cases, it will give me the value K, the scale factor of enlargement. Now, B divided by E would be EK divided by E. That leaves me with just K. And C divided by F would be FK divided by F. That leaves me with just K. So they're the same constant value, and that's my scale factor of enlargement. Now let's try out that SAS rule with this example. Are these triangles similar? I'm not given very much information. I'm not told what any of the angles are, and I've got some of the side lengths labeled. But which of these side lengths correspond to each other? I really don't even know where to start because I haven't got an angle of reference. However, by opposite angles, you should know that these two angles are equal. Angle BCA in triangle ABC is equal to angle ECD. Knowing that those angles are equal, we can see that in each triangle, we're given the side length on either side of that angle. So we've got one matching angle, but are the corresponding side lengths actually corresponding side lengths of similar triangles? Now it's difficult to tell again which of these side lengths correspond. Does the 6 correspond with the 10, or does it correspond with the 15? I'm going to go ahead and make the assumption that the shorter side lengths for each triangle, so the 6, which is shorter than 9, corresponds with the shorter side length of the other triangle, so 10 is shorter than 15. So I'm going to assume that 6 and 10 correspond, and 9 and 15 correspond. If they don't, these are not similar triangles. If they do, well, they are. So let's put 6 and 10 in one fraction and 9 and 15 in another fraction. 6 over 10, is that the same thing as 9 over 15? Well, they both work out to be 0.6, so yes, they give us the constant scale factor of enlargement. So one triangle is an enlargement of the other. Would you think that the side lengths of triangle ABC get multiplied by 0.6 to find the side lengths of triangle CDE? Or is it the other way around? 0.6 is smaller than 1, so if we multiply by 0.6, we'll get a smaller answer. For example, 10 times 0.6 gives us side length 6. 15 times 0.6 gives us side length 9. If I knew what ED was, I would multiply that by 0.6 to find side length AB. So triangle ABC is equal to triangle CDE enlarged by some scale factor, which is less than 1, which explains why it's gotten smaller, 0.6. If I want to figure out the scale factor that turns triangle ABC into the larger triangle CDE, I would have to do my fractions the other way around. I would have to use the reciprocal of the fractions I used. So instead of 6 over 10, 10 over 6. And instead of 9 over 15, 15 over 9. That gives our scale factor of enlargement 1.6 recurring, or 1 2/3. So which sides correspond? BC definitely corresponded with EC, and AC definitely corresponded with CD. We found our scale factor of enlargement. So yes, these triangles are similar. Let's just recap before we get into our practice exercise. Remember that if you're not told that triangles are similar, you should be asking yourself, can you prove any of the following? Do they have all angles equal? Is the ratio of the side lengths of one triangle equivalent to the ratio of the side lengths of the other? Can you find the constant scale factor of enlargement for all corresponding side lengths? And finally, can you prove that they share corresponding SAS? That is, that they have one corresponding angle and the side lengths on either sides of those angles follow the constant scale factor of enlargement. Make sure you've got a good note down and you've got a good grasp of those 4 points before we go on to the practice. So on to the practice now. All I want you to do is tell me if these triangles are similar. If they are, prove it. Tell me which of those rules you can prove. If they're not, explain why not. Explain if maybe they've broken one of those rules. And if you can't prove anything, explain what information is missing. What would help you to either prove or disprove that they're similar? Now be very careful because there's very little values given here. However, you must pay attention to the markings here. I hope you know what these little markings here mean. They pertain to side lengths. Here you've got a square in the corner here. That tells you about the angle. Do you know what angle that represents? Over here we've got these arcs, a double arc in that angle and a double arc in that angle. Similar to these markings on the side lengths, show that these angles are equal. Go ahead and hit pause now. Copy the diagrams. Make sure you explain your answers clearly, referring back to the rules that we've discussed. And hit play when you're ready to take it up. I hope you've taken your time to copy those out carefully and give good details in your explanations, because here come your answers. For question 1, these triangles are both isosceles triangles, so I actually know all 3 sides of both triangles. I can put those into ratios, and I can see that those ratios are equivalent. So yes, these triangles are similar by the equivalent ratios of their side lengths. Question 2 shows 2 triangles, and I hope you knew that that little square meant that they were right-angled triangles. They're the same type of triangle, but that doesn't necessarily mean that they are similar. We only know one angle from each triangle, and although they gave me these markings for the side lengths, that only tells me that this side length here is twice the length of this side length here. But it doesn't allow me to compare these side lengths. So I don't know if this side length here is twice the side length of this side length here. There's not enough information there. We only know one angle. We only know that one side length is twice the length of the other. Not enough information. I would like to know some more information about the other side length so I could do SAS, but I can't prove anything as it is. Question 3, you should have noticed that we have one angle for each triangle, but we don't know the side lengths on either sides of that angle. We could make an assumption to compare corresponding side lengths, and again, I've compared the 9 with the 10 because those are next to the angle, and the 14 with the 15 because those are across from the angles, but that's not a rule. I'm just fishing for some hint at whether or not these are similar. Comparing those two fractions, however, although you may want to say that they're not similar since 9 over 10 doesn't equal 14 over 15, I don't know if I was comparing corresponding side lengths. The 9 might have corresponded with this side length, and the 10 might have corresponded with that side length. So I really can't draw any conclusions about this, and I shouldn't make any assumptions just by looking at the diagram. I don't know. Next, question 1 over here, you should see that I do know actually 2 angles from each of the triangles. I know that the ones marked with the double arc are equal, so I'm calling that X, and I also know that opposite angles are equal, so I'm calling those Y. Because of opposite angles, I have 2 pairs of equal corresponding angles here, which means I must have a third pair of corresponding equal angles. So I know all 3 by angle, angle, angle. These are similar triangles for sure. Question 2 here. I know that they're both isosceles triangles, but that doesn't necessarily make them similar. If I have no side lengths to compare to find a scale factor of enlargement or equivalent ratios, and I have no angles to compare, again, I can't prove anything. In our last example, you should notice that there's a small triangle DMP inside triangle LMN. And notice that these triangles have a shared angle at point M. That is, angle DMP is equal to angle LMP. And if that's the case, we've got a common angle. Have we got corresponding side lengths on either side of that angle? Notice that LM must correspond with DM, and LM is twice the length of DM by those single markings there. Also notice that MN corresponds with MP, and MN is twice the length of MP. You can see that with those double markings there. So even without having any actual values, we can see that by the SAS rule, triangles LMP is an enlargement of triangle DMP with a scale factor of 2. They are similar. So how's that gone for you so far? I know this can be a bit confusing, but for now, just make sure you understand those rules. So how's that gone for you so far? I know that this is difficult to begin with, and I'd be really impressed if you manage to give the same kind of detail when trying to prove if these shapes are similar or not. The main thing right now is understanding those 3 rules. All angles equal, corresponding side lengths that either follow a common ratio or give the scale factor of enlargement, and SAS. Now to leave you at the end of this lesson, I want to show you the kinds of similar triangle patterns we often see on exams. You should be able to look at them without any values given and be able to recognize them as similar triangles. I'd love to see who could tell me down in the comment section why any of these patterns represent similar triangles, even though I don't know any of the side lengths or angles for them. I hope you found this lesson interesting and helpful, and I left you something to think about. Till next time, keep practicing, and I'll see you soon.